Good afternoon, everybody. My name is Thái, and I'm an AI researcher in healthcare from AI for Life at Hanoi University of Science and Technology. Today is very honor for me to be here and present about my recent research about state-of-the-art AI in multimodal medical imaging and future research direction. So this content of my presentation. I will start with a brief introduction about VOM, and then I will move to our initial work on AI PET CT imaging, and then I will discuss about some future research, and finally to conclude with some key messages. So to begin, I will introduce about vision language model, which also known as VOMs. This model is very powerful. That is designed to learn the visual representation combined with contextual language embeddings, so that VOM has capability in cross-modality reasoning. VOM has opened some clinical application in medical context, such as radiology reporting, cross-modal retrieval, pathology localization, and decision support. Several representation models include MedClip, X-ray GPT, BioMedClip, and LavaMed. They have strong research in report generation and medical PQA. However, multilingual capacity of this model remain limited, with most progress concentrated in English. So next, I will continue with a common VOM fine-tuning flow, which can be seen in the LavaMed architecture. Typically, this fine-tuning flow involves two stages. The first stage is medical concept alignment. That is to train the model to associate the medical images with corresponding medical context. And then the second stage is medical instruction tuning, that we optimize the model to follow the medical instruction and give a response about medical task. On the other hand, a wide range of public datasets support this model, though most are still concentrated on chest X-ray, leaving modalities like PETs and CT underrepresented. I can define the main challenge here as the domain shifting problem. First of all, medical images usually have different textual structure and semantics other than natural images. And another thing is that medical texts are richer, more technical, content sensitive, and demand expert level knowledge to understand. So that leads to some existing limitation. The first is that VOMs and dataset recently focused on 2D chest X-ray, 3D CT, and 3D MRI. And secondly, VOMs are largely monolingual, overwhelmingly dominated by English. So that's the specific domain like PET remain largely underexplored. And such low resource language such as Vietnamese is several overlooked. And here's the table about limitation of current VOM in Vietnam is report generating from PET images. We have 3 VOMs and GPT-4o, and we evaluate it done with 4 NLP matrix, Bleu, Rope 1, L, and Bus score. And here's some example of what they respond for the question. So the key finding is that GPT-4o achieves the best performance but still show limited values. That leads to insufficient clinical accuracy. And we are working in highlight the needs for multimodal and multilingual expansion of medical VOMs. And we have proper VIMED PET dataset and comprehensive benchmark in PET report generation and VQA task that's submitted to the NeoRIP 20 and 25. And here's the comparison of our VIMED PET dataset with existing medical business language datasets. We observed that recent medical VOM process relies on data aligning medical image with structured text. And some common modality like CT, MRI, and X-ray dominate the existing benchmark. So that leads to some missing modality problem that PET-CT is significantly underrepresented in current VOM training dataset. And several datasets offer PET and CT volume still lack the pair clinical reports, making them insuitable for generative VOM tasks. So I highlight the need for dataset that align PET and CT imaging with structured clinical text. And here's the illustration about our VIMED PET dataset. We do some de-identify for patient privacy, and we leverage the approach to split the PET-CT volume into 3 body parts. And each PET-CT volume is aligned with corresponding PET-CT report. This dataset is sourced from a trusted hospital in Vietnam over 4 years, and it had over 3,000 complete PET-CT clinical study. And each study has the volume covering from head to upper thigh of patient and corresponding well-structured report. This dataset covers several diseases like lung cancer, thyroid cancer, and a broad range of clinical case. And here are some pre-processing method and device testing of how it is obtained. And to support the training and evaluation of medical VOMs, we propose to construct 4 specialized subsets. We had the VQA dataset, report generation dataset, study comparison dataset, and medical test set that's focused on specific disease, lung cancer. And each subset serves a distinct purpose in model fine-tuning. And we have some statistics of the original dataset and the augmented dataset for training and evaluation. For the VQA dataset, we aim to enable the multi-turn and context-aware dialogue about PET and CT images. So we use GPT-4o few shot prompting to generate the single turn and the multi-turn conversation on diagnostic reasoning and clinical Q&A. And here's some example about the few shot. The Q&A can be the question from the user, which part of the body does this image capture, and the AI will give the corresponding answer. This image capture the chest region of the patient. And for the report generation dataset, we use GPT-4o to paraphrase the original clinical report, and then each paraphrase person is then verified by the medical expert that collaborated with us on this research. And for the study comparison dataset, we asked the GPT-4o to give the similarity and the difference lie between the two medical images that is described on reports. And we also design a clinical evaluation pipeline to evaluate the VONs on real-world scenario. This pipeline has two phases. The first phase that the medical experts define the structural clinical attribute from the report, and then the second phase that we prompt the GPT-4o to extract output from generated and graduate report, and these are mapped to clinical classes for M1 score evaluation. And here's our overall backbone of fine-tuning flow. It had 3 states. The first state is that we fine-tune the 3D vision encoder, and the second state is concept feature alignment. We elaborate the 3D linear projector to map the vision embedding into the clinical language space, and the final state is instruction tuning with low-rank adaptation that we fine-tuning the overall architecture. And then after we obtain the change model, we adapt this to downstream stats like PET-CT, report generation, and VQA. And here's some evaluation. We had evaluate this combination of vision encoder and language model on report generation tasks using both NLP matrix and our proposed clinical evaluation matrix, and also for the VQA task. And here's some demo results of the generated report, and also for the VQA task. So the current achievement here is that the fine-tuned model on our VIMED PET, so significant improvement in both metrics, and we acknowledge the existing limitation lie on the lack of CT modality, and we plan to incorporate this anatomical feature and enhance the medical reasoning of the VOM. So here's some future research approaches. The first that we need to design a cross-attention-based module for visual extraction to fuse the information of both CT and PET. And we need to split the PET and CT report to PET and CT-based description using GPT-4o. And another potential approach is that we can integrate RAG technique to instruction tuning phase. That means we will use a medical clip-based model to retrieve the related medical knowledge during the fine-tuning phase. And recently we have implemented with the combination of CTVAT and Mistral 7B, and here's the new proper backbone of our model. We can see that we already use the information of the CT volume, and we build the 2 additional pipelines to generate both the CT description and the PET description, and then we integrate this to prompt design for instruction fine-tuning in detail. To fine-tune the vision encoder, the first step that we need to use the GPT-4o to split the original PET CT report into CT description and PET description. Description like CT description is only about anatomical information, and PET is functional information. And then we use the clip style pre-training to build the CT encoder and PET encoder to get corresponding embeddings, and then we fuse it using the cross-modality module. For prompt design for instruction tuning, instead of just using the simple question, user question like what is this medical image describing, we also integrate the instruction that The VOMs can also use the PET and CT requisition at optional context for enhancing the information during the phase to generate the PET-CT report. And some initial results show that our new PET and CT model achieved the better result across 4 matrices. So there is a significant potential for improvement. And to conclusion, our initial result demonstrate the feasibility of PET-CT based VOS. So there is some so much room for further improvement. And the key is that the vision language model show promising potential in advanced multimodal medical imaging, and it will support more equitable AI in healthcare. And we encourage the community to explore, build upon, and extend this direction for broader medical impacts. So that's all about my presentation today, and thank you for your listening.